So this over here is the build plate, and this is the 3D printer head, right? So it has two extruders, one extruder here, extruder motor, one extruder motor here, so one left, one right, and two nozzles, so one left and one right. One nozzle will extrude the actual model material. The second nozzle will extrude the support material. So this way you can sort of maximize the speed of the print to be able to print faster, more accurately, and with better support structures. Some models that only have one extruder would generally generate the support structures from the same build material as the base model. So you can see this is where the thermoplastic filament, how it's fed through the machine. It's fed through the machine, you can see all the way through the back and coming out the top over here. I'll tell you what, even the location of the spool, yeah, or the thermofilament, how it's being fed, that can also affect your print. So some thermofilament spools are located on top of the machine because it's easier for the extruder motor to pull down on the filament than to pull it up. When it's pulling it up, it's working against gravity, whereas when it's pulling it down, gravity sort of helps it pull material out of the spool. And also the spool axis can also, if that has a lot of resistance, it's harder for the motor to pull out the material, can affect how well it extrudes or how consistently it extrudes, because that's the whole key, that's the whole trick, that's the main issue with these 3D printers, FDM, is to get a consistent extrusion of material. If the extruded material is not consistent, you cannot control how well it's going to print, and you'll have defects, differences in the layers and in the print, and it can lead to all sorts of issues in your model. So you can see these are the drive wheels. So you have a motor that's moving these wheels over here. So you have one motor moving these wheels and one motor moving these wheels. And these wheels, they grab onto the filament, and as they turn, as they rotate, they push it through the extrusion nozzle. So over here, this is labeled as a liquefier over here, but this is the hot end, right? So we call it a hot end because it has a heating element which heats up this thermoplastic filament for it to become liquid. That's why they labeled it as a liquefier, to be able to get pushed through the nozzle and onto the workspace. So as you can see, this is what I'm talking about. Each layer is produced from these sort of lines, yeah? So the filament is melted and deposited onto the build platform or the build plate over here in tiny lines, right? And the consistency of these lines is what determines how good your model is. So the distance between the nozzle and the build plate and between each layer, this will determine the layer thickness, yeah? And you can also see the hole of the nozzle that will determine sort of the width of the line. So considering you have the width and the height of this sort of tube, that gives you the cross-sectional area of this line that's been extruded, and that will give you the resolution of the print that you can obtain. See, so it laid down some support and some actual thermoplastic material or base material next to the support structure. And then it moves on to the next layer or the second layer and deposits it on top of the first layer that it already created. So as you can see, this support structure was added over here because, right, I'm not exactly sure what they're printing, but you can see it needed to deposit material in the third layer over here, and there was nothing to support it underneath. So if it didn't build a support structure or add support material over here, this layer would have just fallen to the build plate or to the base layer. And that's not what we want, because we wanted the layer to be over here in 3D space. So that's one of, let's say, the disadvantages of FDM as compared to selective laser sintering or selective laser melting, is the need in certain scenarios or certain cases for this support structures. So as you can see here, the build plate is removable. In some 3D printers, this is not removable. In some 3D printers, this build plate over here is heated to sort of help with adhesion of the base layer to the build plate. So the larger the thermal gradient, so if the build plate is cold and the thermoplastic filament is extruded on top of that at a temperature of, let's say 200 degrees Celsius, that's a very common melting or build temperature in FDM. You can see from what's ambient temperature. In certain places it's 18 degrees, in certain places it's 20 degrees Celsius, but you get a huge thermal difference, of at least 180 degrees Celsius, temperature difference. This temperature difference, obviously, as the material cools, it contracts, right? So this plastic filament, the base layer, after it's been printed and, the 3D printer moves on to the next layer, blah, 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 etc. Once it's at layer, let's say like 200, layer 1 has already cooled down a lot. Not necessarily to the ambient temperature of 20 degrees, but something close to it, maybe like 30 degrees or whatever. And by doing so, by cooling down by, that much of, 170 degrees or, more than 100 degrees Celsius, it contracts, not by a lot, but by enough for, if the material contracts on the base layer, it might detach from the build plate. So you want to minimize the amount of contraction of the base layer on actually of all the layers in the model. So to do that, some 3D printers offer a heated bed, which raises the base layer temperature to sometimes like 65 degrees Celsius or 80 degrees Celsius. You don't want to raise it all the way up to the melting point, because then your model will lose its resolution. It will become a blob, or it will sag or melt in different areas. But you want to raise it enough that it can stay solid, and not melt, but enough that you reduce that thermal difference between the melting and, the actual deposited layer. Because the more you reduce that thermal difference, the less contraction of layers you will get, and the less model deformation you will get. So here you can see they've removed the build plate, and they're removing the model from the build plate. And here you can see this is post-processing. So what they're doing is they're removing the white support structures from the final model with a little knife or scalpel or, chisel over there. And this has to be done once the model has been fully printed, and it adds additional time to the manufacturing process. Also adds, additional material costs to use, these two materials, the support material that costs some money to purchase it and to use it. But I think the main cost is in the post-processing, the time it takes to actually remove the support material. And as you can see over there, if we go back just a tiny bit, you can see there's some rough edges, or it's not really smooth where the support material was present. That's because obviously they are both thermoplastic filament. They sort of melt a tiny bit together. Obviously you'd want to minimize that amount of contamination or cross melting between the support material and the actual model, but you can't fully eliminate it. So that would make the surface a bit rougher. You need to post-process it. You might need to sand it down, smooth it off. It requires a bit more time and effort to actually obtain a good part. So you can see over here, this one I'm assuming it was built relatively fast, but you can see, if you look closely, the layer lines in between the different layers, and you can see that the surface of the finished part is not necessarily 100% smooth. Yeah, so this is a consideration that you need to keep in mind. Yeah, this is an element that you need to be aware of when you produce parts through FDM, Fused Deposition Modeling, because depending on your needs or your customer's needs, if you are producing this in an industrial environment for an end user, you might need, depending on the requirements, to either sand this down, or if you're using ABS plastic, ABS plastic can actually be smooth with vapors from acetone, yeah, because acetone actually melts ABS plastic. So nail polish remover, if you get that in contact with a plastic part that's made from ABS plastic, it will melt it, yeah, because there's a chemical reaction over there. So if you have had any experiences where you've spilled some nail polish remover around some plastic parts, you might have noticed that it actually damages them. Be careful with that. But in this application, in the 3D printing community, they have found, different techniques or different ways to actually smooth the surface. And one of these techniques is using acetone vapor, where you put a tiny amount in a cup of acetone, right? And you put the part next to it, and you enclose that into under like a little glass container or any kind of metal container. Like you can put a pot over it, but usually a glass bowl is put above the ABS part and acetone container. And the acetone itself is a volatile chemical. So what that means is acetone sort of turns from liquid to gas. Yeah, it releases an acetone vapor. It turns into gas. So if you leave, let's say, if you put some acetone on a plate, yeah, a tiny amount of acetone on a plate, that acetone will eventually turn to gas and disappear, right? It will, as an example, right, it's not exactly evaporating as water does, but similar to that. It will just turn into gas eventually. So by putting these components with acetone under a glass bowl, you can sort of see the effect that this vapor contained within the glass bowl has on the part. It will slightly melt the surface of your ABS part, sort of blending in all of these layer lines and smoothing the surface, so you can obtain a very nice surface using this technique. Obviously, another method would be to sand the surface of the part, and that could smooth it, in a physical manner, if you don't want to use, chemicals such as acetone, because they can be, dangerous. You don't really want to be inhaling these chemicals or handling them, because there's a risk of dropping the chemicals either on your table or the floor or carpet or whatever is around your workspace. And these chemicals can actually damage other surrounding, parts or areas if you're not careful with them. So if you want to avoid that headache, you can just use sandpaper It's less risky, you know, it's a much safer approach. Also, it's worth noting that this acetone smoothing, yeah, or chemical smoothing can only be applied to ABS plastic filament. If you are using PLA filament, yeah, polylactic acid filament, this cannot be smooth using acetone, so your only option would be to use sanding approach on PLA produced parts, right? So it's also important to take into account what material you are using to produce your parts. Over there, they put it most likely into a chemical bath or, you know, an ultrasonic bath to sort of smooth out these imperfection in the model. And there you go. They're also sanding the models physically over here, right? Either the sanding is to smooth the surface or prepare the surface for painting. See, so this part over here that we see here, this fan blade, yeah, you can see it has a shiny surface, a smooth surface, right? This can be produced through FDM, but only through post-processing. Yeah, there is no way that you can obtain a part with this level of surface finish without any post-processing. So directly produced by an FDM machine, that's not possible. All parts produced via FDM will have a bit of a rough surface. You will be able to see the layer lines. So, but you can also obtain really good surface finish on parts if you invest the time and effort into the post-processing operation. See, and this is obviously in this situation their material bank. So they have all of these thermoplastic filament spools. They have them labeled what it is, you know. So this can be ABS, they can be PLA, they can be, I don't know, different colors, different material grades. They can have different properties imbued. So it can be a combination of, let's say, 70% PLA and 30% wood filament to have a wood grain effect in the final part. It can be, let's say, 70% PLA and 30% metal powder, yeah, to give the material a bit more strength, or to give it, let's say, if you use stainless steel powder, you can give it magnetic properties, right? So the part can be attracted or stick to magnets. Can have, I don't know, glow in the dark powder if you want your end parts to glow in the dark, and so on and so forth. There's many different kinds of filaments, colors, options available for FDM. See, so this is kind of a few samples of different materials that they've produced via FDM, right? So as you can see, they've 3D printed a case for a controller using FDM 3D printing technology. So using this technology, you can produce parts for many different applications. You can produce prototype parts, right? To test different concepts that you may have, or to test designs, or to see designs physically. And then later on, using those prototypes as a base, you know, produce final end user parts. Or you can also produce end use parts using this technology. So that controller case that's been produced, you know, if it was properly finished or processed, where it's been sanded and painted, or, you know, clear coated, that could be used as an end model, right? It doesn't have to be a prototype. It can be an end use part, right? This can also be used, you know, in industry to make, as we've discussed, jigs and fixtures to align different components. It can be used even if you wanted to, let's say, in the medical industry to produce, I don't know, hand braces. If you broke a bone and you need a cast, this can produce customized cast directly to fit your body or to fit you perfectly, rather than using something, more traditionally where the size might not be 100% fit for purpose for each individual. Yeah. So we have covered selective laser melting, selective laser sintering, fused deposition modeling. Let's move on to stereolithography. So as you can see, this is more of an accurate representation of the size of FDM 3D printers and SLA 3D printers that are available, let's say, for in the consumer market. So for hobbyists. The previous size of FDM 3D printer that we saw, that's more of an industrial grade 3D printer. So it's much larger, much more bulky. It's harder for, irregular people to obtain it, like hobbyists, yeah, because it requires a lot of space, it's more expensive. But something like this, and obviously this is for SLA, but there are similar FDM 3D printers of similar size and even cheaper price than SLA that you can have, own at home, use at home, and produce models. But as I said, the features, resolution, and whatnot that you can obtain from these cheaper models or consumer models might be more limited than the industrial grade models. So also, what you have over here, I don't know if you can see it really well, but there is in stereolithography, right? There is the resin bath container over here. So this bottle, that's the resin that is the base material for the models to be produced. You pour that resin over here into this container or receptacle. This build plate that you have over here that's currently moving to the top will dip down in there, leave a tiny gap, and there's a laser here underneath that shines through clear glass plate onto the resin, onto the build plate, which hardens the resin, and the build plate will move slowly upwards, pulling the model out for each layer while the laser hardens each layer. I believe we'll see that in this video. So you can see this is a resin receptacle, so you pour the resin inside of it, and it has just a transparent bottom through which the laser is shined. And as you can see, that little dot, that was the laser that was shining through the resin, sort of hardening each cross-sectional layer. That's the build platform. Obviously, it's removable to be able to help you remove your model from the build plate. One thing to mention, because it's using lasers, UV lasers and whatnot, this cover that was just opened, that is a laser blocking cover, to avoid damaging your eyes with the laser and whatnot. And obviously resin is toxic, so you'll have to rinse your model afterwards. We'll see that in this video. That's the clear window that we just saw that the laser passes through. See, so the resin tank was filled up, and now the 3D printer starting its print, it's dipping the build platform within the resin. And that was the laser sort of tracing each layer cross-sectional area to harden it. So now this is after the print has been completed. It needs to be rinsed. Over here, they're using isopropyl alcohol or rubbing alcohol or general disinfectant. Yeah, generally it's the 99% isopropyl alcohol that you can use to sort of remove the resin. You can also use distilled water if you wish. Obviously, depending on the resin that you use or the resin that you purchase, there will be instructions and guidelines on how to rinse your parts, because it's a given with stereolithography that you will have to post-process in terms of rinsing. One key concept is, if you do not rinse your parts by exposing these parts to sunlight, the liquid resin will get hardened by sunlight itself, because sunlight has UV rays, and these UV rays that are present in sunlight can cause the actual thing that causes, sunburns. That's from the UV rays. So obviously the laser itself, because it uses UV technology, it can be dangerous for people, especially for their eyes. So you have to be really careful using this technology. And right now, what this fellow is doing, he is post-processing. He's removing the support structures from the model. So obviously, because resin bath, there's nothing actually supporting the model between the build plate and a layer, if you haven't actually you don't have an element of the model underneath that layer. So as per FDM, in certain instances, you will need to have some support structures just to support your model. And these need to be removed as well in this instance. So there you go. As you can see from the initial not post-processed model, there were a lot of support structures that needed to be removed. And this can be very intricate. It can take a lot of time, a lot of effort. And if you make a mistake, you can potentially damage your model, right? The actual piece that you want. So as we've mentioned in the main body of the course, you want to avoid post-processing as much as possible. But as you can see, this is an end model, and the surface of the model is very smooth. The resolution produced via stereolithography is very good, much better than FDM, right? You get no stair stepping, you don't get a rough surface finish. And also, because these layers are chemically hardened, right, using UV lasers, the bonds in between layers are also much stronger. So these parts can be stronger in the build direction than through fused deposition modeling. Because in fused deposition modeling between layers, because there is a lag for the build plate to reset to the next layer, there is cooling for the previous layer before the next layer gets put on top. So the bonding between layers, it's not the best. And as you can see, because this is a polymer, yeah, it's a resin, depending on the thickness of the part, it can also have some element of flex to it, right? And I believe you can also get some different types of resins that are different types of polymers that also can affect the surface finish, the color, the amount of actual, let's say, how solid the model is, the hardness of the model. So you can actually obtain some resins that produce softer models and some resins that produce harder models, right? And considering this is a laser, this uses a laser, the resolution can be actually much more precise. It can be, the laser, let's say, thickness is thinner than human hair, right? So that's the extent of the resolution that you can obtain using this technology. It's sort of the same with selective laser melting, but that depends more so on the, let's say, particle diameter of the metal powder, right? Over here, because you're using liquid resin, the determining factor is the laser itself. And selective laser melting, the laser also has an effect, but usually the laser can be more, let's say, accurate than the metal powder itself, and the laser can produce a thinner cross-sectional area than some of the metal particles themselves. So let's move on. So you can also make some parts that are, let's say, more robust or stronger, such as this carabiner. We've mentioned this already in the main body of the course as one of the applications of stereolithography, right? You can see what they've done over here is they've produced a model of a ring out of resin and polymer. And what would happen in the jewelry making industry is they would put this ring in some sort of material like sand-like material, right, as a base, because sand has good, thermal properties. It can resist a lot of heat. And what they do is over here on the base, they bury it upside down in the sand to produce a mold. And over here on the base, they would pour the liquid silver or liquid gold or any other type of molten material. And this molten metal would burn away all of this, polymer or resin and take its place. So it take the shape of the ring within the sand or within the mold. And see, you can end up with very intricate details on the ring and such fine, components or fine pieces. So this is one of the industrial applications of this, among some other applications as per fused deposition modeling.